Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss cooling due to adiabatic demagnetization. Let's begin. Cooling. How cooling is considered? Many attempts have been made to attain very low temperatures of the order of 0 temperature. One such attempt was made by using the phenomenon of liquefaction of gases. Attempts of cooling. First attempt, liquefaction of gases. What is liquefaction of gases? When temperature as low as 200 Kelvin could be attained. This is the liquefaction of gas. Means we have to attain the temperature as low as 200 Kelvin. This is one attempt to cooling. Another attempt is to reduce the temperature was made by boiling of helium under normal pressure. Here we get the temperature of order 4.2 Kelvin was attained. This is one attempt of cooling. This is another one attempt of cooling. But now, later on, that liquid helium under reduced pressure could attain a temperature as low as 1 Kelvin or even less. Later, liquid helium under reduced pressure, this is the normal pressure, that is under reduced pressure, we get the temperature as low as 1 Kelvin or even below. These are the three attempts of cooling. Now, to produce still lower temperatures, means to produce the temperature lower than 1 Kelvin, the method of cooling to produce below 1 Kelvin temperature, the method of cooling is known as that cooling by adiabatic demagnetization, that is cooling. The method is known as cooling by adiabatic demagnetization of paramagnetic salts. The cooling by adiabatic demagnetization of paramagnetic salts is the method of cooling to produce below 1 Kelvin temperature, and this process was proposed by two scientists. One is Debye and another one is Gaikiu. The two scientists proposed the method of adiabatic demagnetization for cooling. Due to that method of cooling, we get below 1 Kelvin temperature. These are some attempts to get the cooling procedures. So, what is adiabatic demagnetization of that of paramagnetic salts? Take a look here. Heating effect is observed using the process of adiabatic magnetization. Heating effect is observed using the process adiabatic magnetization. And the cooling effect is observed by the process of adiabatic demagnetization. The entire process means the heating due to adiabatic magnetization and the cooling due to adiabatic demagnetization is known as thermomagnetic effect. These two are combiningly known as, we say it as the thermomagnetic effect. Heating effect due to adiabatic magnetization, cooling effect due to adiabatic demagnetization. Combiningly these two effects is known as thermomagnetic effect, or we can say it as the magnetocaloric effect. Let us look how the adiabatic demagnetization is for that of paramagnetic substance. Look here. If we consider a paramagnetic substance, here let a paramagnetic substance. This is the paramagnetic substance. And this paramagnetic substance is when we don't apply an external field. It has a number of tiny magnets and these are the random arrangements of tiny magnets inside that of paramagnetic substance. Here no external magnetic field is applied here. The net magnetic dipole moments when no external magnetic field is applied is 0, as all the dipole moments are randomly oriented as shown in that of figure. And here M is 0 and S which is greater than 0. Magnetization is 0, S is the 0. This is the demagnetized paramagnetic substance. When we have magnetized, means the paramagnetic substance is magnetized, means we apply an external magnetic field here. So the tiny magnets are aligned as far as the application of external magnetic field is concerned. So this alignment due to that of external magnetic field, and here that paramagnetic substance will magnetized, and the randomness means the entropy will be 0 and it is magnetized. Here that one is demagnetized. So if same paramagnetic substance or paramagnetic salt is placed in a strong external magnetic field, that magnetic field be the B vector with the external magnetic field B. So then the magnetic dipole moments tends to align in the direction of external magnetic field as shown in that figure. One can apply that magnetic field of the order of 2 to 3 Tesla. If on the application of external magnetic field, the magnetic moment M change by a small amount dm, and the work has to be done by the system, that work is known as the magnetic work, that we have studied in that of previous video lecture as magnetic work. So then the external magnetic field has to do some work on that of substance, and the work done here, the work done that is dW is given as B dot dm. So that is B dm cos 180 degree, cos 180 that is 1, that is minus 1. So minus B dm is the small work done dW. If during this process total heat is kept constant, then that process is known as adiabatically. If heat is constant, then that process is treated to be as adiabatical one. Then due to the rise in internal energy, its temperature must rise. Rise in internal energy tends to rise in temperature. On other hand, if that process temperature kept constant is known as isothermally, then some heat must leave that a paramagnetic substance and its entropy must fall, means temperature increases and entropy falls. The substance gets demagnetized. On isolating that system and switching off that magnetic field, that is why the work done by that of substance is taken from the internal energy of that of substance, and the temperature of that of substance falls. And due to the application of that of external magnetic field, that demagnetized paramagnetic substance is now magnetized. Let us take a thermodynamical explanation of the process of cooling due to that adiabatic demagnetization. How cooling is found out from that of adiabatic demagnetization. So, the thermodynamic explanation here, thermodynamic explanation for that of cooling due to adiabatic demagnetization. The thermomagnetic effect, as we studied here, heating effect due to adiabatic magnetization and cooling effect due to adiabatic demagnetization is combiningly known as thermomagnetic effect or magnetocaloric effect. Due to that thermomagnetic effect is used for cooling substances whose initial temperature is less than, which is equal to 1 Kelvin. At this most low temperature, all substances are in solid form, and so the volume does not change during that of process. So, right here, during thermomagnetic effect, during thermomagnetic effect, what happened? At very low temperatures, all substances are in solid form. All substances are in solid form. So, the volume does not change. Since they are in the solid state, so their volume is treated as constant. Volume does not change, that is, change in volume will be 0 here. Therefore, the small work done dW is equal to PdV, that is the mechanical work, plus magnetic work, and that magnetic work will be BdM, that is the magnetic work BdM. Since dV is constant, so the work done only due to that of magnetic work, that is minus BdM. Now, we have to use the first law of thermodynamics here. Using first law of thermodynamics, first law of thermodynamics, dq is equal to du plus dw, or we can say that is the pdv. Right here, that is dw. Here dq is equal to TdS. Using the second law of thermodynamics, T with the temperature, ds with the change in entropy. du in place of dw, that is minus bdm minus bdm. Here let we compare that equation to the standard equation of first law of thermodynamics. Means the first law of thermodynamics, in place of dw, that is pdv. So, Here let we compare it. Comparing this equation to standard equation of first law of thermodynamics. Standard equation of first law of thermodynamics. What we have? First law of thermodynamics is dq is equal to du plus p dv. Let we compare. dq is equal to TdS, du is equal to du. Here p play the same role as minus b and v play the same role as m. So pressure play the same role, pressure P play the same role for that of minus B, and volume V is replaced by that of M. That's why now applying Maxwell's thermodynamic equation, Maxwell's thermodynamic equation. Maxwell's thermodynamic equations are elaborately studied in upcoming video lectures. So stay tuned with this for more information regarding Maxwell's thermodynamic equations. So del T by del P at constant entropy is equal to del V by del S at constant pressure. Look at that equation. dq or TdS is equal to du plus pdv, means I just write here that is TdS is equal to du plus pdv. So taking as entropy as constant, so we have del T by del P at constant entropy is same as del V by del S at constant pressure, that from Maxwell's thermodynamic equation. Let we replace, in place of M with V and minus B with P. So what we get? Replacing this, so minus del T by del V constant entropy is equal to del M by del S at constant B. Now multiplying T on both sides, temperature, so minus T del T by del V constant S, so T del M by del S at constant B. We know that T del S by del T is equal to Cb. Here we know that T del S by del T and constant entropy is equal to Cb, that is specific heat at constant magnetic field. Specific heat at constant magnetic field, at constant magnetic field. So here del T by del V del T by del B constant S, T is divided here, so minus T by T del M by del S at constant B. Now I take the chain rule here, so del T by del B at constant S minus T by T using the chain rule, that is del M by del T at constant B and del T by del S at constant B. So del T del S by del T at constant B, here is the constant B, and the specific heat at constant magnetic field. Now that is del T by del B at constant S is equal to minus T divided by, that is T into del T by del S. So minus T, that is Cb del M by del T at constant B, that term, that is T into del T 1 by T into del S by del T, that is Cb here. Now del T for a small adiabatic change dB in that of magnetic field, the corresponding change in that of temperature will be how much? So dt is equal to minus T by Cb del M by del T at constant B into dB here. That above equation gives the rate of change of temperature with the change in that of magnetic field in that of adiabatic process. So here we have to use, take as a equation, take as a equation number. Here we know from the magnetic susceptibility, that is Xi, which is inversely proportional to that of temperature, and magnetic susceptibility is per unit volume. Magnetic susceptibility is the ratio of magnetic dipole moment, at the ratio of magnetic dipole moment to that of external magnetic field B, and when we remove that proportional, we use the proportionality constant, let that proportionality constant be K by T, where K is the constant, where psi is the susceptibility, that is the magnetic susceptibility, and K with the constant known as Curie constant per unit volume, Now differentiating with respect to T, what we get? So it will be M is equal to K times B by T. Now differentiating this, with respect to temperature, we get, that is del M by del T, whereas B taking as constant, minus Kb by T square. Now putting the value of del M del T r constant be where? In that of equation number 1. What we have? Now putting this value in equation number 1. Now putting this value in equation 1, we get, in equation 1 it will be dt is equal to minus t by cb minus kb by t square into dB. Just put that value. So our dt is equal to, that is 1 t cancel out, kb minus minus plus kb cb t dB. So t dt, t is multiplied here, so t dt is equal to kb by cb into dB. Now integrating both sides of that of equation by taking the initial and final values of t as t initial and t final, and the initial value of b will be b and final value will be 0, that of b as b and final value will be 0. So assuming that the specific heat of that of paramagnetic salt at constant b to be the constant, so integrating the above equation, by using proper limits, we get, that is t dt, that is temperature initial be Ti, that is initial temperature, and Tf be the final temperature. Here is the K Cb as constant to outside, and integration from initial magnetic, that is B will be, but final it will be 0. So B in dB. Here I write Ti the temperature at initial, Tf at the temperature at final. Now integrating that one, we have T square by 2, using that of limit Ti to Tf, here K by Cb, again that will be B square by 2, using the limit from B to 0, or that is half T f square minus T I square is equal to K by 2 Cb, again that is 0 minus B square. So half cancel out on both sides, it will be T f square minus T I square is equal to minus K B square by Cb. Therefore T final square is equal to T initial square minus K B square by Cb. So look at that of a particular expression, that negative sign in that of a expression concludes that from that of equation, from this equation, T f square minus T I square is greater than 0, since negative sign appears. It means that that term will be less than 0. that implies that the final temperature is always less than that of the initial temperature. Final temperature is always less than that of initial temperature. So, what indicates that particular cooling system? So, from the above mathematical analysis, we conclude that the conclusions we have drawn here. Thus, cooling is produced. Thus, cooling is produced due to adiabatic demagnetization. Due to adiabatic demagnetization when the external magnetic field B is reduced to 0. When the external magnetic field B is reduced to 0, means we demagnetized that particular magnetic material. That is why the cooling is produced due to adiabatic demagnetization. So, with the help of this video lecture, we understand how cooling due to that of adiabatic magnetization. These are some attempts for cooling, and that is proposed by the scientists Debye and Gaiker. That is adiabatic demagnetization, cooling by adiabatic demagnetization. And what is thermomagnetic effect or magnetocaloric effect? Then how the paramagnetic substance which is demagnetized and then it will be magnetized by applying some external magnetic field. And next we discuss thermodynamic way to explain that of cooling due to that of adiabatic demagnetization. So, we proceed. Use that of first law of thermodynamics and Maxwell's thermodynamic equations and the concept of magnetic susceptibility. And finally, we show that the final temperature is always less than that of initial temperature, and we conclude the cooling is produced due to adiabatic demagnetization when the external magnetic field B is reduced to 0. So, with this useful and informative notes, let me wind up this session. Thank you.